So today's topic is factoring. We want to work on how to transform an equation in the standard form y is equal to ax squared plus bx plus c into an equation that is comprised of two binomial terms. So an equation that has two terms that have two terms each, rather than this three-term equation. And so we want to know why we want to do that, and then how to do that, of course. So the reason we might want to make an equation into this kind of form, into its factored form, is primarily for two reasons. One, let's say we have an equation, trinomial, that is the numerator in one equation, and then we also have a denominator here that might also be another trinomial. What we could do is, if these are factorable, sometimes we'll find that we can actually write this as an expression of binomials, and that some of these terms will cancel out. They'll be equal. And so we can rewrite this as a much simpler equation. Now, another case might be that we want to find the roots of our equation. What this would mean in our realistic example, sort of, would be if we had a graph where the y-axis is the speed of our vehicle and the x-axis is our time. And we measure out how fast this vehicle is traveling, over whatever period of time. And so finding our roots would be, we want to know on this equation, this is y is equal to whatever. We want to know at what times was y equal to 0. So that would mean for us, when is our speed equal to 0? When is the car standing still? So those are the two things that we would want to use factoring for generally, the most common things anyways. Then we want to know, how do we actually go about factoring something? So we'll start out with our first example that I've got written off to the side here. We have y is equal to 6x squared plus 11x, is that correct? Yes, plus 3. And so, let's see, we know why we want to factor this, or why we might want to factor this. And then we want to know how we can factor this. In order to get into that, we have a few things we need to check first. Is this set up properly for us to factor? And then can we actually factor it? Because we don't want to waste our time attempting to factor an equation that we ultimately cannot factor. So first thing to check is this in order for factoring? So currently it is. We have it in the general form, ax squared plus bx plus c. But we might see this equation written as 3 plus 11x plus 6x squared. We can still work with it just the same. These are both equivalent. It's just that this new form, this is much easier to work with than this, just because it's all switched around. So we want to get it written into this, just this general form. And then next we want to see one more condition before we check if we can actually factor it, and that's, is there a common factor between all three of our terms? So can we factor something out to simplify this equation? Currently, the greatest common factor is just 1, and so there's no factoring we need to do. We're all good to go. But if this was, say, y is equal to 6x squared plus 12x plus 3, well, now we have a greatest common factor between each of our terms that we can remove. So, or not remove, that we can factor out. So then it would be 3 here, and we're left with 2x squared plus 4x plus 1. And then we're in a good situation to start working with it. Now, the last thing we want to check before we get into directly factoring the equation is, can we actually factor it? Because we don't want to waste our time here. How can we check if we can factor it? Well, there is a value called the discriminant, which is represented by a triangle. It's capital delta. And this value is equal to b squared minus 4 times a times c. So this value here will allow us to tell whether or not our equation is actually factorable. And the way we'll know that is if our delta, the ultimate value that this is equal to, is a perfect square, which means if we can take the square root of whatever delta equals, and if that number is a whole integer, so like 1, 2, 3, 4, 0, just a whole number, then this is indeed factorable. If it's not, if it's, let's say, delta equals like 4.5, then the square root of delta would not be a whole number, and thus it would not be factorable. So we want to substitute our values for this example in and determine if this is factorable or not. So first we have delta is equal to b squared, which is the coefficient in front of our x, so that's 11 squared, minus 4 times, and then a times c is going to be 6 times 3. So for us, that gives us delta is equal to 121 minus 4 times 18, which I believe ultimately gives us 64. Check if that's correct. It does not, it gives us 49. So delta is equal to 121 minus 4 times 18, which is equal to 49. So we want to know, is this number a perfect square? Yes, it is. The square root of 49, if we take the square root of both sides, we get that the square root of delta is equal to positive negative 7. These are whole integers, so really we would just take, the one we're considering is 7, positive 7, because if your delta is negative and just negative, then you're not going to be able to factor it with real numbers. So really we're just looking for, is the square root of delta, can it be a positive whole integer? In this case, it can be, and so we're good to factor. So now that we've checked our example, we can finally get on to how do we actually factor this. Now that we know it's in the proper order, we've factored it if it can be, or we've removed the greatest common factor, and we've checked that it's factorable. So how we actually factor this, we have this cross, or this x here, these 4 quadrants that we'll put 4 values into, which will allow us each time to get our factors for an equation that we have already deemed is factorable. So in general, I'll do the general form over here, and then our specific example over here. We have these 4 quadrants. In this top one, we're going to input b, our coefficient for our x term, and in the lowest quadrant, we're going to put a times c. So that's our coefficient here, and our value here multiplied together. On our specific example, we can go ahead and substitute these in. Our b is going to be 11, so we'll have 11 here, and then this is going to be a times c, so 6 times 3, that's going to be 18. Now over here we'll have 2 more numbers, number 1 and number 2. How do we get number 1 and number 2? Well, we get number 1 and number 2 by finding 2 numbers that satisfy these 2 conditions. The first condition, A, is that number 1 times number 2 is equal to a times c. Our second condition, B, is that number 1 plus number 2 is equal to b, our top number here. And so the easiest way we go about doing this first is we find our factors of a times c. So in our example, we want to find what combinations of numbers will multiply to equal 18. Well, that would be 1 and 18, 2 and 9. I'm going to go ahead and erase these here. 3 and 6. And of course it could be negative 1 and negative 18, negative 2, negative 9, negative 3, negative 6. It just depends on what's up here, and we'll see some examples later where we involve more negatives here. So for now, since it's positive, both top and bottom, we're most likely going to be looking for positive factors. In this case, we know these multiply to a times c, so our first condition is always satisfied. Now we just need to find which combination of these will add up to 11. Well, what jumps out to me is 2 and 9. 2 plus 9 is 11, and so those will be our number 1 and number 2. Now how do we decide which one goes in which blank? Doesn't matter. So we can have 2 here and 9 here, or we can have 9 here and 2 here, and we'll see why that works in just a second. So I'm going to go ahead and clear this off. And then now we want to rewrite our equation using the information we just got here in our sort of x thing. So I'll write this over here. We're going to begin by carrying over our ax squared term. It's going to be the exact same. 6x squared And now the only thing that changes is instead of writing our bx, so 11x, we're going to write number 1x plus number 2x. So our general thing would be, let me write that a little clearer, plus number 1x plus number 2x, and then our c would carry over just the same. So plus c. Now for our inputting our specific values here, that gives us y is equal to 6x squared plus 2x plus 9x plus 3. So what you should notice is that if we've done our sort of cross here correctly, these two equations should be equal to one another. If you notice, we add number 1 and number 2x, that's 2x plus 9x, which is 11x, and our other terms remain the same as well. So that should always be the case, no matter what. The next thing we do, I'm going to go ahead and erase this and move the work over here. The next thing we want to do is we want to group together our terms into binomials. So those terms of two terms. So we have 6x squared plus 2x plus 9x plus 3. From here, we want to find in each of these terms the greatest common factor amongst those two terms and factor it out for each one. So in this case, our greatest factor in 6x squared plus 2x is going to be 2x. So we have y is equal to 2x times 3x plus 1. We're going to do the same thing here. The greatest factor that I see is 3. So we factor a 3 out, that gives us 3x plus 1. What you should notice is that these two terms should always, 100% of the time, be equal. If these aren't equal, then something's gone wrong in this step if this was already correct. So the last thing to do here to have this fully factored is group these two terms. What we'll see is we have 2x of this term plus 3 of this term, the same term, meaning we have 2x plus 3 of that term, or 2x plus 3 times 3x plus 1. And that's our fully factored equation. What we can do from here is one of those things I mentioned earlier. We want to find the roots of our equation. That's usually why we're factoring it, so I'll show that here with this example. If we want to find the roots of this equation, that would be equivalent to saying we want to find the x values whenever y is equal to 0. So we set y equal to 0 and then rewrite our equation here in terms of x. So 2x plus 3 times 3x plus 1. The reason factoring this trinomial into an equation of binomials is useful for finding our roots is because of something called the zero product property, which means if you have two terms, a times b, which equal to 0, then that implies that either a equals 0 or b equals 0 or both a and b are equal to 0. So what this means for us in the context of factoring is that if, I'll rewrite that, if our, let's say our first term 2x plus 3 is equal to a, and our second term 3x plus 1 is equal to b, if a is equal to 0 here, that would mean this is equivalent to saying 0 is equal to 0 times this, which would be true because 0 times this would be 0. The same thing applies if this term was equal to b, then it would be, this would be the same as saying 0 is equal to 2x plus 3 times 0, which is true once again. That would be 0 on that side. So that zero product property allows us to do what we're about to, which is we set each of these terms equal to 0. So that allows us to write 2x plus 3 is equal to 0, and 3x plus 1 is equal to 0. From here we just solve for x to get our roots. So we have 2x is equal to negative 3, and x is equal to negative 3 halves from there. And then 3x is equal to negative 1, x is equal to negative 1/3. And these two values are our final roots. We know at these x values on this equation, not this equation, on this equation, y will be equal to 0. So that concludes how we factor our example here. now we're going to work on 5 more examples, or I believe 4 more examples that cover a bit different circumstances that you might factor a trinomial in. So we'll get started with our second example, and that is y is equal to 4x squared minus 12x plus 5. Yes. So the first thing we want to check, as per our previous thing, whatever it is first, is this in order? Yes. So we have our ax squared plus bx plus c form. We're in order. Next thing is there a common factor between all 3 of our terms that we can factor out? Yes, there is. It's just 1, so we're good to go. If it was like 2 or whatever, then we would factor it out and move on. For this one, it's already good to go. So next we want to check, is our discriminant a perfect square? So remember, b squared minus 4ac, is that a perfect square? So for us, that means delta is equal to negative 12 squared minus 4 times 4 times 5. Work this out. This gives us delta is equal to 144 minus 80, which means delta is equal to 64. Well, we know the square root of 64, that's equal to positive negative 8, and so positive 8 here is what we're looking for. Delta is equal to, or the square root of delta is equal to a whole integer. This is factorable. So now we want to factor this. We'll have our little x here. So remember, b goes in this top quadrant. For us, that is negative 12. Then we have a times c in our lowest quadrant. That's 4 times 5, which is equal to 20. Now we want 2 factors, so 2 numbers that multiply to 20, but that add to negative 12. Here's what I was talking about earlier with having negatives and positives mixed in. Since this is positive and this is negative, that's going to imply for us that we want 2 negative factors, because 2 negative numbers will multiply to a positive but add to a negative. So both our factors will be negative here. We can start listing them out. Negative 1 and negative 20. We'll have negative 2 and negative 10, negative 4, negative 5. Now we want to see, well, we know each of these combinations multiplies to 20, so which 2 of these numbers, when added together, will equal negative 12? 2 and negative 10 jump out. So we know these suffice. Negative 2 plus negative 10 is equal to negative 12, and then negative 2 times negative 10 is equal to 20. So those are our factors. We'll write them here, negative 2 and negative 10. And again, it doesn't matter which order you write it in. This could be negative 10, this could be negative 2, which I think I forgot to show in my previous example, still works. So I'll show that on this one. So let's get started rewriting this. We know it's negative 2, negative 10. So we can rewrite our equation as 4x squared minus 2x. Remember that negative, or that number 1 comes here, and then minus 10x, that number 2 comes here as the coefficient for x. Our c stays the same. And if you had written negative 1, or if you had written your x as negative 10 and negative 2 instead of negative 2 and negative 10, you would have written this equation as y is equal to 4x squared minus 10x minus 2x plus 5. And I want to show you that either way works. It doesn't matter if we've done it correctly. So now we're going to group our 2 terms here, or group this into 2 terms. So we'll have 4x squared minus 2x plus negative 10 plus 5. And then on this equation, they're both equal to each other, but in a bit of a different order. We'll have 4x squared minus 10x plus negative 2x plus 5. All right, remember we want to factor out the greatest common factor from each of these terms. On this equation, it will be 2x, so we'll have 2x times 2x minus 1. And here we can factor out a negative 5, so we'll have minus 5 times 2x minus 1. You should notice these, again, are always equal. In this case, we can factor out a 2x, so it leaves us with 2x minus 5. And on this, we can factor out a -1. You can see that they're very similar. That leaves us with a positive 2x minus 5. And again, these two terms are equal. Last, we want to group them. So we'll have 2x minus 5 times 2x minus 1. And then here again, we'll have 2x minus 1 times 2x minus 5. These are both equal. They just have their order of terms flipped. And then we can solve for the roots here if that's what we'd like to do. So in this case, we'll have y is equal to 0, which would imply that 2x minus 5 is equal to 0, and 2x minus 1 is equal to 0, giving us x is equal to 5 halves, and x is equal to 1 half, and that looks like a 6. That's a 0. Those would be our roots. Same over here. So now we will get on to our third example here, and we'll just show it one way again, since we showed that both ways work there. Our third equation is y is equal to 2x squared plus 3x plus 7. So, running through these again really quickly, our equation is in standard order. We have no greatest common factor other than 1, so we're all set up there. Now we want to check, is this factorable, so we don't waste our time. You might notice if we start filling in our b squared minus 4ac, we'll get 3 squared, which is 9, minus 4, times a times c, which is 14. This number is actually equal to 9 minus 56, I believe, which is negative 47. Well, here we just have negative 47. We don't have negative and positive 47. So even though this is a whole integer, this is less than 0. And so when that happens, if we were to factor it, we would have imaginary numbers because the square root of negative 47, oh, that's right, my mistake. Even if this was like, let's say negative 49, the square root of that would be 7i, where I is equal to the square root of negative 1. It's an imaginary number. We can't factor this over real numbers because it's less than 0, even if this was a perfect square number. So since our delta is less than 0, for our purposes, we can't factor this. So we've saved ourselves some time in terms of factoring this. We just can't. This is where we would use the quadratic equation. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. We would substitute our values in from the standard form, and then we could get our roots that way directly. You'll notice this value probably looks familiar. That's our discriminant. So this value we just can't factor, so we'll move on to our fourth example. Right, number 4. Y is equal to 1/2 x squared plus 3/2 x plus 1. So the only thing that's changed up here is that our coefficients for a, b, and c, or just a and b, those are fractional. What we want to do is we want to get these into whole numbers if we can. In this case, in order to attempt that, we would multiply our equation through by 2. So first, if y is equal to 0, otherwise it would become 2y, but here we're going to have y equal to 0. So 0 times 2 is still 0. 2 times each of these terms would be, now we just have x squared plus 3x plus 2. So we've multiplied through by 2, and we find that we have, in this case, a really nice whole integer coefficients for our trinomial here. Now we can check there is no greatest common factor, so we don't need to pull anything out. And then our equation is in order. So we can go ahead and check now, is this factorable? Well, our delta here is b squared, which is 3 squared, equal to 9, minus 4 times a times c, which is 1 times 2, so 2, giving us delta is equal to 9 minus 8, which is equal to 1. Well, the square root of delta then is equal to positive negative 1. So positive 1 is a whole integer, and that means that this is a perfect square. So we're good to go. This is factorable. Let's go ahead and do that. Should have kept that. Y is equal to 0 is equal to x squared plus 3x plus 2. So we'll construct our x here, and we'll fill our values in again. So b up here, 3. Down here we have a times c, which is 1 times 2, so 2. Well, we have essentially one factor here, which is 1 times 2. We could explore positives and negatives here, but you'll notice 1 plus 2 add up to 3. And so we just know our numbers right here for 1 and 2, which lets us rewrite our equation as 0 is equal to x squared plus x plus 2x plus 2. And from here we can do, again, we can group our terms. 0 is equal to x squared plus x plus 2x plus 2. We'll factor out our greatest term from each of these, which gives us x from this, so x plus 1. And we factor out a 2 from our second term, giving us x plus 1. These two terms should always be equal, and we can finish this grouping here. So we have x plus 2 times x plus 1. From there we can solve for our roots. This gives us x plus 2 is equal to 0, and x plus 1 is equal to 0. So our final roots are x is equal to negative 2, and x is equal to negative 1. And then we can move on to our fifth and final example. So here this is going to be y is equal to x squared minus 5x plus 6. X squared minus 5x plus 6. In this case, we just have 1 as our a. This is the first example we've seen of that, where it's off the bat 1. So again, we're just going to follow our standard procedure here. This one you'll see you can probably, with enough practice, start doing these in your head, especially with the leading coefficient as 1x squared. We'll stick with our little x method here. So we want to input, or first we want to make sure, is this factorable? So our delta really quickly is b squared, which is negative 5 squared, which is 25, minus 4ac, which is 4 times 1 times 6, which is 24. This gives us delta is equal to 1, which as we know means the square root of delta is equal to positive negative 1. So this number is a perfect square. That's greater than 0. So this is factorable. So we're going to go ahead and construct now our x. So we have our b up here, negative 5, a times c, which is 1 times 6. And here again we have that disparity in signs. So since this is positive down here and negative up here, it means we need two numbers that multiply to a positive but add to a negative, meaning we'll have two negative terms. So the factors here would be negative 1 and negative 6. They could be negative 2 and negative 3. Well, we know negative 2 plus negative 3 is equal to negative 5. So that will give us our values here. We'll go ahead and rewrite our original equation as x squared minus 2x minus 3x plus 6. And we'll begin doing our grouping once again. And we'll go ahead and move through this a little more quickly. So we'll have x times x minus 2 and minus 3 times x minus 2. Group these together. Y is equal to x minus 3, x minus 2. And then we can set that equal to 0 and get our roots here. So 0 is equal to x minus 3, 0 is equal to x minus 2. And then we can finally solve for our roots, which are x equal to 3 and x is equal to 2. So we went through that one a little quickly. what I mentioned earlier was that since this has a 1 leading ahead of things, it might just be easier to factor in your head because you can just start looking at just those last 2 numbers and thinking, once you know that it's factorable with our calculation of delta, look at these and say, well, what 2 numbers multiply to -6 and add to -5? You might see off the top of your head, -2 and 3 will suffice. And since our coefficient's 1, we don't have to worry about having extra things in front of the x here. It'll just be 1. So this is kind of the nice, easy, fun case. And those are all of our examples for factoring trinomials today. Hopefully this helped. Take care.